Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to Eccentric Mold and Engineering's webinar, Rapid versus Traditional Manufacturing. My name is Connie, and I'll be your host for the session. A few things to cover before we start the webinar with our keynote speakers. This presentation is expected to last approximately 30 minutes. Q&A is included during the presentation, so feel free to submit your questions using the chat function located in the lower right-hand corner of the control panel. With that, I'll now turn it over to our keynote speakers, John Sidorowitz, Glenn Miller, and Darwin Rowe. Gentlemen, please tell us a little bit about yourselves.
Good afternoon, and thank you, everyone. This is John Sidorowitz. I am VP of Inside Sales and Customer Service here at Eccentric Mold. Glenn?
Hi, everybody. I'm Glenn Miller, tooling engineer. I'm working for Eccentric for a year and a half. I've been working in injection molding design for about 25 years.
I'm Darwin Rowe. I'm a senior project manager here at Eccentric. I've been in the tool business for about 25 years.
All right. Thank you, guys. We're going to get into it. So the agenda for today, kind of highlighting rapid versus traditional manufacturing, plastic part or injection molded part development process, benchmarking criteria, and then just kind of highlighting the traditional manufacturing process as well as the rapid manufacturing process. So kind of highlight the difference between the two. So rapid versus traditional, you've got faster process steps in between with the rapid manufacturing process. There's better efficiencies. It's more economical from a pricing perspective. It can lead to new market discoveries and optimize your learning curves and untapped revenue streams much, much faster. So and what we got here is kind of a crude process of creating a plastic part or a design or whatever it may be, a widget. It starts with the design phase, moving into prototype testing, and then iterations of that, and kind of cycling back through until you end up with your final product. So in the design phase, you're going to be looking at geometry, tolerances, your materials, your textures. What does this part need to do? How does it need to function? How does it interact with other parts? And so forth. And then from there, you kind of move into prototype phase. In this case, we're referring to the prototype in regards to rapid manufacturing, injection molding, not necessarily 3D printing. So kind of go into tool design, tool build, molding of parts, and then inspections. And then once you have your parts, again, more inspections, testing, form, fit, function. How does it interact with the assembly, other parts, and then moving into any engineering changes or iterations, which again just kind of restarts the cycle over until you have your final product and move to production. Anything you guys want to add to that?
Well, just at that end phase there, it's the key parts. All of it's key, but when you get to the testing, the tryout stage, you're doing your fit and functions, making sure the parts working the way you want, mating with other pieces, and then you go in and the task then is to make small changes, materials, parts, the tooling itself, to get you to a tighter tolerance on the part that you're trying to create.
Okay, good. So just some benchmarking criteria for when you're looking at suppliers. Nowadays you've kind of got three main supplier types: your traditional injection molders, rapid injection molders or quick turn, and then your marketplaces, which may be brokers or kind of go-betweens or China. Another thing to look at is timing. How much time do you have? What are you looking to do? How much time do you have from design completion to order placement? order placement to first shots, and then, how much time do you have for iterations and everything in between. And then lastly, and probably most important, is cost.
Right, and you want to obviously balance all of these things. Your timeline, when you need to get this prototype piece into the next phase. We have so much time to design a tool, we have so much time to build it, and we have so much time to make adjustments and do different iterations. So it's really a kind of a time versus cost balance.
Right. All right, so we're going to kind of focus on the traditional manufacturing process. So I'm going to go over these points here. So with the traditional process, you've got many steps in the approach. There's a lot of safeguards and monitoring in place throughout the entire process. And you got various steps for testing form, fit, function, and discovery of part flaws. It's more manual than a rapid manufacturer. And then if modifications are required or something's found out, 3 or 4 weeks down the line, it's difficult to get back on track again. There's a lot of time lost.
A lot of steps, a lot of different people, different areas that need to have a say in that process. So it does kind of drag out the process a little bit.
And with the traditional manufacturers, you're mainly dealing with steel production tooling. It's a good mold material. It just carries higher costs and longer lead times. But with that, you get higher volume part production.
You get more durability in your tool. We use a pretty high-end aluminum in the prototyping process, which holds up very well. But the steel tools, will hold up longer. But there are cost and timing issues related to that.
Yeah. And we'll kind of just walk through kind of a normal process for a traditional injection molder. So it starts off with a manual quote. Someone's going to kind of take that file, review it, and put everything together for that production tool or that traditional tool. And again, do a DFM analysis, which is all going to be a separate step in the process. Then an order's placed. Typically, it's going to be mailed or sent in or faxed in. Next step is going to be mold design. So the mold designers will take the CAD, do another review. And at this point, if there's any issues found, they may send back for requoting or redesign or anything like that. And anything like that is, if any of those happen, it can cause delays kind of going backwards. And this sometimes can be a lengthy part of the process, the back and forth on design and how things are going to be, ejector pins, gates, and things like that. So once the mold design's approved, you move into the mold manufacturing. Parts are molded, and then inspection happens. So the parts may be shrinking abnormally or have something wrong with them. May need to go back into design to address some issues. And it kind of circles back through mold design, manufacturing, parts being molded and going to inspection until the part is correct. Typically, you want to match to a print at that point, and then the parts would ship out. With the rapid manufacturing process, it's a little bit different. It's a lot more streamlined. There's a lot more automation and in the process. So, submitting a file online, doing a DFM and communicating, via email or digitally.
A lot of times during this phase, this is where you're going to see a lot of the feedback from the prototyping phase and in any other iterations before you went into a production tooling project. So there's going to be a lot more input so we can avoid any kind of issues that may have come up during the initial prototyping stages.
Right. So it's similar to the traditional. It's just a little bit different process. Like I said, mainly it's going to be cost. So cheaper cost. There may be a little bit of give in regards to quality, but that makes up for speed and cost in most cases. If you need a part in hand, in 2 weeks, 1 week, you can get that part in hand and be working with it compared to 6 to 8 weeks or something like that.
Right, and that's with the understanding that it may not be perfect, it may not be exact to a print,
right?
But you're going to get that to market a lot quicker.
And get to your issues quicker and figure out any inefficiencies in the design or the assembly. That way you can make your iterations much, much faster and get that product out. So as Glenn had mentioned earlier, traditionally, with our process and other rapid manufacturers, we utilize a QC10 aluminum, which is a high-grade aircraft aluminum for our molds. It works well for prototyping, bridge tooling, and low-volume production. It has excellent strength-to-weight ratio. It's good for managing heat. And the costs, just compared to steel, not only for the materials and cutting is much less. It's recyclable. Really the only con with it is it can break down over repeated use. Long runners or running, high abrasive materials like, high glass content filled materials. But with Eccentric, we do offer a lifetime mold guarantee. So that really shouldn't be an issue. So here's kind of the same process we looked at earlier. It's just, again, more condensed. We're talking days now instead of weeks. So, with Eccentric, you can, upload your CAD model and get a DFM and, order pretty much within 24 hours if you're ready to go. Once the order's placed, we're designing that mold in 1 to 3 business days. We provide a PEG, which is going to show your parting line, ejection, and your gate locations. And once that's approved, it's the tool's being made. And again, kind of there. This is standard timing, not any expedited timing, which we do offer. So, typical mold build times is 3 to 10 business days. Then we have 1 to 3 days for molding parts and inspections, 1 to 3 days, depending on what's required. We kind of do a la carte in regards to inspection. It's really whatever the customer needs. Actually, kind of forgot about all that. Sorry about that. And at that point, we're shipping out to you, and then you have the parts in hand. You can do your own validations, your own inspections, really whatever you need to do with those parts at that point.
At that point, you'd be provide us with some feedback on, the part's great, except for these couple of little areas. The color wasn't exactly right. Whatever little issue you have, whether it be cosmetic or dimensional, that feedback comes back to us, and we address the tool accordingly, tool check it for accuracy to make sure we're where we're supposed to be according to the CAD model, and just proceed from there to try to dial in your parts.
All right. If you guys got any questions, please submit them so we can get to those right at the end here. Darwin, anything yet?
No, I'm good. You guys are covering it great.
All right. Well, I guess we're almost at the end. So kind of in summary, the traditional process has got many steps and a lot of validation steps. So your time to market is going to be longer and higher costs. Versus a rapid manufacturing process. It's going to be more efficient. You can save potentially on inspection time, cost, and time to market. But again, there are some pros and cons. You may be giving up a little bit of quality in some cases, not all.
Really just depending on the complexity of the part and what the expectations are from the customer. Again, between traditional tooling and quick turnaround. It's weeks versus days to get this mold into a press and get you plastic and have you inspecting and checking your parts and providing a game plan, providing any kind of feedback for change.
And we do go through the same steps. We just have it streamlined towards faster paced.
Mm-hmm.
As Glenn says, it's days, not weeks.
Okay. What kind of brings us to the end here? And looks like we've got a question already. So the question is, are the rapid versus traditional molds typically less complex, straight pull without lifters or side actions? No, I mean, with the rapid manufacturing process, you can do complex molds, multiple undercuts, insert molding, over molding. It's typically going to be done in a manual manner instead of automatic slides or lifters. But we can do automated tools as well. It's really going to come down to the geometry. So, a more difficult or complex part might have a standard lead time of maybe 4 weeks compared to a standard 3 week. Anything you guys want to add to that?
No, it really comes down to, traditional tooling. You have slide pulls with traditional action, hydraulics, traveling lifters, all sorts of things that really are difficult to do in a short time period on a prototype tool. So we can do the same type of undercuts, same type of features with hand-loaded, as John said, manual type of tooling. And then you can move on to your, for longer production runs, you can move on to more automated tools.
Okay, so we're getting a lot more questions. What are the surface finish limitations with the rapid process? Really with the aluminum, we really can't go any more polished than like a SPI A2. And then as far as graining goes, we can do just about any grain with the aluminum tools.
Whether it's blasting or laser etching, we've done some pretty nice texturing on our aluminum tooling, and it holds up pretty well.
Mm-hmm.
With the aluminum too, you're not going to have like your traditional lens. It's not going to be crystal clear. It's going to have a little wave to it, as opposed to like a steel lens that's polished.
Yeah. Is this only for small parts or tools? Can you do larger projects? Yes. We can do, larger parts. Our max footprint size is 24 inch by 24 inch with a max depth of roughly about 5 inches or a 30 ounce shot size. So we can do bigger parts all the way down to pretty small, roughly 1/4 inch squared. How many units can you print using a mold? I'm assuming how many parts shots can you get out of a mold? It's really going to depend on the material and the design. But again, with us, we guarantee the mold for life, so it is unlimited.
The more parts you plan on producing, perhaps the decision is made to then go to a higher cavitation on a tool. So those can all be looked at during the quoting process.
And then we got here, what are the steps of moving from a prototype process to a production molding process? It's a good question. We like to design the tool in a manner knowing that it's going to go to production. That way it can be replicated. And we have worked with production molders in the past, and what we've learned on the tools and the designs and helping, kind of do the handoff there. So hopefully that answers that question. You mentioned textures. Are there any textures available, or is that going to add to the lead time with the rapid tooling? Depending on the texture. So we have standard kind of in-house textures. We can do, anything from a SPI C3 to an A2. Then we have kind of a light bead blast and heavy bead blast, which we can do in-house, which really wouldn't affect lead time. Now, if you were looking for, some sort of custom texture, custom graining, that would add to lead time.
And that can sometimes go for any type of lettering, etching that can't be machined CNC. Sometimes that will also need to be textured as well.
Correct. Are you able to do high temp resins such as PSU or PPSU? Yes, we can. The mold may have to be built a little bit differently to accommodate, heater rods, but yes, we can. And then looks like someone just asked the same question, but for Altum, yes, we can. Let's see what else we got here. I think that's about it. As far as mold costs go and the costs for lifters or actions, it's really going to be design dependent. Really can't put a number on anything. I know there's a couple questions that ask about costs. If you have a design ready to go or close to ready, feel free to submit it through our website. And one of our sales engineers will be more than happy to take a look at it and give you an estimate and some feedback. Looks like one last question here about PVC. That is one material we do not run. We run soft PVC, but not rigid PVC. We will run the soft PVC in small amount or small batches or small runs.
Okay, well, thank you everybody for joining our webinar today. For any questions or interest in Eccentric products, please visit our website, social channels, or contact us directly at the number email listed on your screen. It would be our pleasure to assist you. Thank you. We hope everybody has a great day.
Thanks, everyone.
Thank you, everyone.
Have a good day.